Okay, I'd like to start by thanking the organizers for the opportunity to talk here. It's very nice to have a workshop on computational and mathematical neurosciences. And my talk is the last, and so I will benefit from the previous talk because the model has been described quite a bit in the afternoon. So the goal is to analyze the collective dynamics of a population of excitatory neurons, spiking neurons, according to their intrinsic properties. So I'll start by presenting the neural network. Then I'll give some numerical intuitions about the phenomena I want to describe mathematically. Then I'll provide the mathematical results and discuss some open questions. So basically, I would like to come back a bit to why is it interesting to study mean field. I think Etienne and Eva spoke about this, but to me, this is nice because we have a rigorous limit with the proof, and we can control most of the time the approximation. I think William showed us some very nice results about this. So using central limit theorem or large deviation principle. And already we can see that although we have a very simple case, a toy model, the mathematics behind it are not very simple. So that's why I think it deserves some investigations. And also from the point of view of tuning the dynamics, it helps for the prediction, to predict dynamics of a finite size system. And so I think one of the earliest success stories for integrated fine neurons is from Brunel et al. In the early 2000s. And recently there's been a renewed interest in those mean field limits using Ott and Townsend, and that's which propelled more studies like Nicola or Augustine in 2017, Divolo more recently, and so on. But all these studies mostly rely on integrated fine neurons. And if we want to have more interesting, let's say, intrinsic properties or intrinsic firing of the neuron, the canonical model, aka the Hodgkin-Huxley one, is too difficult to study, to control the flow, etc. So what we're going to do here is we're going to use a revamped version of the integrated fine neuron model, which is very, very well known. It's called the Brett-Gersner model or the Izikevich model. It's characterized by two unknowns, so the measurement potential V and the adaptation variable W, which basically describe the collective behavior of the ion channels in a very simple manner. The dynamics is very simple. So you have V dot equal F of V minus W plus some current, and adaptation variable is linear. And so F, what is important here is on the right side, you have type of dynamics that you can see. So in this case, it would be bursting. And F is an explosive nonlinearity, for example, exponential. So this small ODE to the ODE explodes in finite time, and the time of explosion is the time of spiking, and then we reset the two variables. Okay, so that's very roughly the line dynamics. We'll discuss it more later. And so at this stage, we introduce noise. Okay, so it gives us a lot of noise can be seen as a free parameter. So it gives us more freedom to analyze the system. So here, like Eva was showing, and more precisely also, more closely, Etienne was showing this also. So each neuron I will spike at a rate, in this case, lambda of V, where lambda is, let's say, the exponential function. And when such a spike occurs, so stochastically at MTS, what we do is the potential of the neuron I is reset to some reset value W, V bar. But the adaptation variable W is incremented by a positive amount W bar. Okay, so that's the dynamics of the isolated neuron, and the potential of the other neurons are incremented by a synaptic coupling constant J. So this is very similar to what Etienne was showing 2 hours ago. Okay, so we can rewrite this using independent Poisson measure the only thing I want, so it's been shown in previous talks. So only notation I would like to stress is that the variable V0 and W0 are IID and of low mu. Okay, so if we want to go to a mean field limit, what we do is we choose a specific synaptic coupling, which is J over N, where J is a constant. And so if what is the limit then? It's very easy to guess what it could be. For example, in this case, for the V potent, for the equation for V, everything is black, does not depend on N. So if it has a limit, when N goes to infinity, the black term will remain. And indeed, this is what we write here in the limit below. And this term has been shown at least 2 or 3 times, will converge to in some sense to the mean of this integral. So this come up with the J over the mean firing rate of the population. So the coupling term arises as a drift. Okay, so this is the mean field that we're going to study in this talk. It is a stochastic limit because we have this Poisson process, for example, here. It's called Makin-Vlasov equation, and it's nonlinear because the right-hand side depends on the full law, of the process itself, and not just on its value. Okay, and so less formally, you can describe this also by saying that you solve the isolated neuron in between its jumps or in between its spikes, but with an added contribution from the other neurons, which appears as the expectation of the rate of the firing rate. Okay, so now that I've described the limit and the network, I need to say just a few words about the individual or deterministic dynamics of the neurons. And you can see it on the right side. Here you have the Wiener line of this vector field. So where the vector field is vertical, you have the W0 line, which is a line here, where the vector field is horizontal, and you have the reset line here. And so, for example, if you start from the reset line, you go to the left, cross the Wiener line, vertically, you go down up to the horizontal, let's say, a null line, and then you are in the spiking zone, boom, you explode in finite time to the right, and then you reset, and the dynamics settling. So this, if F is quadratic, it's called the Izikevich model. If it's quartic, it's the model by Tubul. If it's exponential, it's the ADEX, the Brett-Werner model. So it's very well known. It's the dynamics, the underlying dynamics is quite rich. Pretty much all known firing pattern not seen in biology can be reproduced by this model. Okay, and so here you can see some general assumptions on F. So let's have a look at numerical simulations to have intuition. So if you simulate the law of the limit process, so it's a nonlinear equation, a nonlinear PDE. So we do it here with let's say a finite volume method, and most of the time you observe, at least when the connectivity strength J is small, that you converge to an equilibrium or stationary solution. So you converge, for example, to this picture, and then it does not evolve. Okay, and it's very nice because here the dynamics can be read directly. So you can see the Wiener line is red. You have the green line. You have the intersection of which are deterministic fixed points. So the dynamics wants to go there, and because the firing rate lambda is non-zero, you have a non-zero probability of spiking here, stochastic spiking. And if you spike, you reset. If you spike immediately, you reset a bit more above. Higher, and then in between you have some. You see that the dynamics takes place, and you go back to the equilibrium. Here you can see that marginal on the reset axis is well confirmed by Monte Carlo simulations. But now, if you increase the connectivity strength, what you can see periodic orbits. You have an example here where the mass is the same. The mass goes this way, goes up, and go for a round trip like this. You can see that the mean membrane potential oscillate like that. So you can see these periodic orbits quite easily, numerically, I mean. And finally, the last point is if I try to compute the equilibrium, the stationary distribution, depends on your field, but stationary distribution or equilibrium of the PDE or stationary states, if you want to, whatever you call them, if you want to compute them as function of the connectivity strength, you observe that when the connectivity strength J is small, these states seems to be stable. It's shown in green here. When J is high, this is puzzling to me. I don't know how to prove that. There seems to be no equilibrium. I cannot prove this, but numerically, I've observed this many times. I don't know how to show. And in between, when it's red, it means the distribution the stationary distribution is unstable. Usually, you observe a periodic orbit. Okay, so that's it for the numerical gateway. Now, I would like to discuss the mathematical results. So the first thing is how can we solve the mean field equation? How can we make sense of this equation? I just rewrote the equation for the membrane potential here. And so here there's a very old trick that's been shown by Etienne. If we play the dummy, so it means if you are given this interaction quantity, we call it, let's say, A, so it's a non-zero, it's non-negative, let's say, continuous function of time, okay? And so we replace it formally here. So this is the equation of an isolated neuron, okay? It's still stochastic, but receives the contribution of the other neurons, which are deterministic. And if we are able to solve this one, and A satisfies the self-consistency equation, meaning that A is equal to the mean finite rate times J, then we have this provide solution to the nonlinear equation. Okay, so it's very classical, and so we must therefore characterize the finite rate that I write R, which is the mean finite rate. Okay, if you multiply by J, it should give you A. So let's study this equation first, the isolated neuron one. It's a bit technical because the vector field explodes in finite time. And so after the time of deterministic explosion, there's nothing happening. So we have to ensure that the neuron, the isolated neuron, spikes before this time, okay? And so it's very classical, but basically you have to ensure that this integral equals to infinity, where F, I remind you, is the explosive nonlinearity of the vector field of the membrane potential. And if you do that, then you can have a solution to the isolated neuron. It's almost obvious because we know the law of the first spike, which is written here. You integrate the rate over the trajectory. So you just flip a coin, draw a number, draw this first spike time, evolve the dynamics, and so. So we have an increasing sequence of jump time, spiking time, and so what can happen is basically analogous to OD. We can have blow up. So we can have an accumulation of this spiking time in a finite interval. Okay. So here I would like to give you a glimpse about the proof of why this is not possible. So we call this property regularity of the process. And so if we use a contradiction argument, so it means we have, let's say, such a trajectory with an accumulation of the spiking time. So let's say that limit of Tn converge to a finite, let's say, 2 to 1. So the interspike interval goes to 0. And then there's a very nice thing about the model here. It's because you can have a look at what is the value of W just after the spike. So when it's reset, and it is a Markov chain by itself, and so we can study it. And so it means we've replaced the full system to a 1D Markov chain. And so now imagine that we have this explosion, so accumulation of a spiking time in a finite interval. What you can prove, it's very easy. If you spike and you spike right away, you will be incremented by W bar. So Wn will be basically W bar times n. So it means that the sequence Wn will be unbounded. And then you can prove that for n large enough, you cannot leave this space, which is a P2. So you stay very high, okay? The dynamics cannot go back like this. And so once you're there, once you have these two property, because the fine rate lambda is non-decreasing, it means that between two spikes, the fine rate is bounded by the value on the reset line, so lambda of V bar. And with this, you can this is basically the basis of the arguments, which show that accumulation of these spikes, it's impossible. Okay, it's embedded into the formulation of the neuron. And so you can prove this also when the current A is not constant, I forgot, but is a continuous function of time and non-negative. So basically with this, we have solved the isolated neuron equation. So now the next thing we want to do is, can we take the expectation of lambda of V? Does it make sense to compute this? Is it allowed? Under which condition? And once we will have solved this equation, we will be very close to solving the non-linear, the mean field equation. Okay, so that's the last step here. So let's X be the solution of the isolated neuron. How can we find this fine rate function? Well, it's relatively technical, but if you write the strong Markov property of the process at the time of spike, you can write an integral, a Volterra equation for this fine rate. And what you see is in this Volterra, this is basically the law of the first spike. So it's analytical, we know it. So we know this one too. And then the rate function appear in the integral of the integral here, and it's the value after the spike. So it's always on the reset line. So it means that's very nice, because if I restrict X to be on the reset line, this is a closed equation. And so instead of being an equation with X being 2D in the full plane, I can restrict X to be just on a 1D axis, the reset line. Okay, so this is very nice. And I think it's parallel to the fact that you can study the embedded Markov chain WN. And so here, if you add one more argument, one more assumption, which is basically this quantity, this function has to be bounded as function of V. So if you remember first, I have to ensure that basically this integral goes to infinity when V is large. And so now this is bounded under this assumption. But I ask now that this product is bounded as well. Then you can solve the Volterra equation. And so it makes, and you can also prove that the solution is continuous in ST. Okay. So it means here, sorry, I come back. We have been able to solve this equation, prove that it's well defined for all time t. So the solution is regular. Under a stronger assumption on the rate function lambda, we can compute the mean fine rate. And so now we can solve the equation, and this is a cheat. I'm cheating a bit here because I'll solve a simpler equation. I introduce a delay term, so in the coupling. And so if I want to solve this mean field, which is very similar to the one, but much simpler, if I do it on 0D, this thing is basically the initial condition. So it's given to me. Then this is the equation of an isolated neuron. Then I can solve it. I can take the mean of this quantity according to what I've just done here. And then I can solve this equation on D to D and so on and so forth. Okay, but for this scheme to work, you need more than basically the initial condition being integrable against the fine rate function. Okay, so we know how to solve this equation, the mean field. We know how to make sense of it. And so now the next question is how can we study the invariant measure of the nonlinear of the mean field? And so loosely speaking, I would just remind you that invariant distribution, stationary distribution, equilibrium of the nonlinear Fourier-Planck, they are more or less the same the same notion, but for different backgrounds. And so if we're looking for a solution that where the law is invariant in time, it means that basically this quantity is invariant. It does not depend on time. And so I'm looking for laws such as alpha is constant, and I have an invariant distribution for this isolated neuron. So the invariant distribution of the isolated neuron for a very well-defined alpha are also the nonlinear stationary distributions. So how can we study them? That's I would like to quickly go over this. This is a very bad slide, but the idea is, as before, we can restrict to the embedded Markov chain, which is 1D chain. And for this one, we can compute the transition operator. We have it basically analytically, it's written here. And we can lower bound the probability of transitioning to specific states, okay? And this is called local doubling estimate. So we have here the formal statement. And this parallel very nicely the proof of Perron-Frobenius. And so if you have this type of estimate, then either if you have a Lyapunov function for your system, then you can conclude that you have an invariant distribution. So we have one, which is basically given here. There is another way to do it here is basically an iterate of the embedded Markov can satisfy global doubling conditions. But what we have as a result is the isolated neuron as a unique stationary distribution, which has a density with respect to the Lebesgue measure. This density is continuous and bounded when, for example, W is large enough, and we know its asymptotic behavior. We know that it's not compactly supported. We know that it has an exponential tail. And from the study of the embedded chain, we can then conclude that this process now itself, not just the embedded chain, the process of the isolated neuron is positive Harris recurrent with an invariant distribution that is given explicitly here. Okay, so we know very well the isolated neuron, and I can give you a glimpse about now. Can we prove that the mean field has a equilibrium, let's say, nonlinear stationary distribution as well? In this case, the current now satisfies a nonlinear equation, which is written here, where T1 is the law of the first spike, and mu W is the invariant distribution I just described. And so what we do, this is parallelizing some recent work by Canizo and Michler. We prove that the function, this function is continuous. Okay, so we show that basically this mapping is continuous in a weighted space, where V is a Lyapunov function. And when we have this, we can apply intermediate value intermediate value theorem to conclude that when J is small enough, there is a solution to this equation, and so we have a nonlinear invariant distribution. Okay, that's all for the results that I wanted to present. I would just conclude. I think we have a good understanding of the isolated neuron. We have a nonlinear solution, a solution to the mean field when the delay is non-zero. The numerics are okay to the point that we can perform numerical simulation and numerical verifications at the level of the PD. So now there are some open questions, very tough. Do we have solution to the mean field without delays? When vector field is polynomial, it's possible based on a priori estimates. But when the vector field is exponential, this is quite tricky. I don't know why. There's something like a blow-up phenomena I cannot control. Same for the existence of nonlinear invariant distribution when J is large. I don't know if there are any. Basically, it pertains to the study of the invariant distribution of the isolated neuron when the incoming current is large. And so this is very tough. I mean, we can analyze it maybe using singular perturbation theory. And it properly scale, it seems to be basically converting to a Dirac, but this deserves a lot of work, and it's very difficult. So with this, I would like to thank you for your attention, and I'll take any question. Thank you.
Thank you, Romain, for this very interesting talk. I'm sure we'll have many questions, despite the fact that it's over 5:30.
Hopefully.
Okay, let me try one. In order to prove that you have a fixed point I think it was, well, I forgot the slide number. You have to prove that some measure is continuous with respect to A. Can
yes.
Can you give us an intuition as to why this is true? It's not obvious to me.
It's not obvious at all. Well, there are many. The first point is so to do that we apply using global estimate, global Dublin estimate. It allows you to apply a Picard theorem in the space of Radon measure with total variation. That's first thing. And then if you want to have so the invariant distribution is a fixed point of the adjoint of the transition operator. If you want to have this fixed point a continuous function of a parameter, you have to apply a Picard parameter version of the Picard theorem. And so what is important is to have first the fact that the adjoint of the transition operator is contracting. That's okay. But uniformly A, so that can be done. But it has to be continuous. And this is tricky. And not only it has to be continuous, but it has to be able to integrate TA, and TA is not bounded. So that's why I could not use the total variation norm, but I had to use a weighted norm because basically TA is smaller than V. Okay, so that's the overall argument.
Okay, well, thank you for this illuminating answer. Any other question? Well, if not, nothing on the internet. Yeah. Oh, okay, so we can split now. And thank you again the speakers of this afternoon.